If sea level rises, there are absolutely nothing good which can come from it. So that is really the threat. So therefore, it's good to say something about it. Sea level changes, facts and fiction. This is my name, that's my institute, and then a few things which tells that I happen to know what I'm talking about. Sea level changes, the facts are to be found in nature itself, certainly not at your table or computer or making strange statistical analysis. Sea level changes, what we call eustacy, 5 basic variables. It's simple like that. Climate change, ice, not ice, and that makes the water go up and down in the ocean basin. Tectonics, the basin has a volume, but if tectonics change the volume, sea level goes up and down. Simple like that. Then you have a bunch of things here which changes where the water level is sitting. And you have the so-called the gravity potential surface. It's a relief of 180 meters. If you go from New Guinea to the Maldives, you come 180 meters closer to the Earth's center of the Earth, which is remarkable. But it's the zero, or it's the potential of water, so it's no uphill or downhill. Then you had the sea surface topography, the departure from the gravitational potential surface, which is in the order of 2 meters and so. That's the steric. The heating comes in here, but also the currents. The Gulf Stream has a bulge of 5 meters. So think of a happy dog which is waving the tail. The same thing with the Gulf Stream, 5 meters bulge going back laterally. This is an enormous thing in local sea level changes. And you have the rotation, which is a strong effect. If Earth speeds up or slows down, the water is flushing back and forth, east-west. But it's, of course, in the distribution for the polar to the equatorial region, it is 21,385 meters. It's a very large thing. So then we have the observational facts. There are numerous factors which has to be considered. And this is usually what people are not doing. They're very, very simple-minded. So if this is change of the shore, it can be dynamic at the shore. It could be changes in the land level or changes in the sea level. And each of those variables are controlled by so many things. If you see, for example, erosion, they usually shout and say, it means sea level is rising. Absolutely not at all. It could be sea level lowering. Often this is the case. And for example, compaction here in the land level is very, very important for the site-specific position of a tide gauge. Because usually it's sitting on a big harbor construction, especially in earlier days. And that had a large load, and all the sediments underneath it slowly compacts, okay? So you have a subsidence stone instead of a tide gauge. And then we come to those really sea itself. It's steric, it means the temperature changes, the basin volume changes, it's a long term, and the gravity potential and the glacier, of course. So then we have a psychological part in it. Sea level changes. Yeah, I'm down here, I'm a scientist. I want to record, I want to understand, I want to work with it. But then there are other group we want to glorify the model. And that is, for example, the global loading model, Peltier-Lambic, the global loading model, Gaia. We have to come back to that. And the global warming model, IPCC, and their, note the wording, Boy Scouts. Because this is really what it is. Those who want to support daddy, you know? And they get so much money for that, and they are so happy. So now we go to the things. So this is what it's all about. Observation fact, again, we are here. This part is more or less, it doesn't matter the difference here. But here it's a very large difference, discrepancy between some people up here and some people down here. And then we could be also in the middle. So we have to pinpoint that. So we go to the present sea level, okay? And the present sea level may change. What would change is if the ocean volume would increase due to glacial melting, if the water column would expand due to heating, if water masses would move laterally, current rotation. All these factors can be handled as to rates and amplitude. That's very important. We can handle those. And now I will go back to one by one. Okay? So we take the glacial volume changes. Glacial volume changes. So this is meters and this is rates, 10 meters. So when we have the maximum ice melting after the Ice Age, about 10,000 years ago or so, that was the maximum melting. We had rates of 10 millimeter per year. I use that as a frame because there is not a chance, not the slightest little chance of beating that frame. So if we want to play with sea level, we have to play inside these frames. That's the only place where physical laws and the historical knowledge allows you to play. If you would violate those things, you can play outside here. Ramsdorff and other, and Hansen, this, I mean, I nearly have to use the word idiot, because at Heath 4 meters in 20 years between 2080 and 2100. It's just unphysical. So we have to play inside that. And remember this, in the last 300 years, we have down here, IPC is there. So frames has to be put there at it. So nothing up here. This is outside the frame is not realistic. Then we go to the expansion of the water column. We have the water column, and we have the expansion, and we have the temperature. Okay, in the ocean, 5 temperature, which is far too much, 2 temperature, 1, and then of course we can never ever heat up 6,000 meters ocean column. We can just play in the upper 700 meters, maybe up to 2,000 meters. But earlier days, we had 700 meters, and 40 years brought you up here. That means 4.5 centimeters at the most. Okay? Argo meeting, which is the new one, they have 0.01 centigrades, and that is just nothing. We are 3.5 millimeters. We should remember something which is absolutely vital, but people don't usually understand. When we come closer to the coast, the water column becomes smaller and smaller and smaller and smaller. And that means that if you have 10 centimeters, which is for 300 meters, when you take that to a level where it's 100 meters, all the shelf areas, you can never be up there. You have to be down here. So it's 3.5 centimeters. If they come where it's 10 meters water column, it's 3.5 millimeters. That's just nothing. And when you are at the very shore, here, it's 0. Of course. I mean, of course. It's just so simple. So you have the abyssal, the shelf, the littoral, and the shore, 0. So these are the things which you are playing with. Out in the open space, maybe a few centimeters, but it's not a rate which continues with time. It's something which is a short-term oscillation. And if you go to the record, ocean heat, this is the ocean heat, which 0.4 centigrades this period, it could be 4.5 centimeters. But Argos, which is much more improved, it's an excellently better tool. We are on 0.01, and this is the reading, and that is where it fits up here. Okay? And then we come to the water distribution, and at the El Nino years in 99, 98, but this is time. You see, you have high here, low there, and within 9 months, or it's a normal pregnancy, okay? This is a high here and a low there. It's a distribution of water which changed. And much of this is a momentum transfer between the solid earth and the hydrosphere. So those are the 3 things which we can work with. But of course, this is not unidirectional. It's not unidirectional. So if we have some tide gauge there, it's not going there for 100 years. It's annual, or at the most decadal. Maybe, and it's not centennial either. So these are the things we have to play with. And then, next thing, how can we assess global sea level and measure the site-specific sea level changes? Okay. I take you through these things. It's a hard and terrible game, measure or assessing the present sea level. The site-specific, we have coastal morphology, a fine tool if correctly applied. Tide gauges, we have one big complication, that's local compaction. Subtracting the crustal component from a tide gauge. We have such possibility in Venice, we have it in Perth, a few stages. Okay? We know what is going on. And then on the regional scale, regional coastal morphology, it's a fine when available. We have it in the Indian Ocean, I think, and I will show it. And mean of scattered tide gauge. NOAA has now 204 sites scattered all over the world which they use. And that if they are actually measuring, so let us use it. Why should we discard it if it's measured values? And we have subtracting the crustal component. We can do that trick. We can do it in the North Sea, and I will show it in your Kattegat. And we can down to very, very, very strong, fine figures. Earth rate of rotation, that is really fine for the post-Little Ice Age sea level rise. But it doesn't work now, if you can, which is also satellite altimetry. It's an interesting and very fine tool, but it's invalidated by their corrections. And I will try to show you. Gravity, GRACE, it is also the same correction, but it's also at the experimental stage. Global loading models, it's time to question those. And I will try to take you through. So all those things, A, 1 to 3, B, 1 to 7, I will go through with you. So A1, coastal morphology, fine tool if correctly applied. I would show you Maldives, Bangladesh, and Goa. Okay, this is the sea level curve. And these are something where you look at the coastal information. Here we have something we call Queen's Bath. It's a lagoonal area. You see a high level here. You see another here, it's abundant today, and the present high tide level and mean tide level. 1, 2, 3, and this is 20 centimeters higher, and it has it's from 1790, because we have also here a peat, and we have dated the change here when it goes out to a lake, and when the lake dried here and other things happened. This 60 centimeter higher level, it's this beach ridge, it's dated 415, and another date here. And so you have it there, and this is the one. You have a peat layer. And then we come to the things here. Here we have erosion. And IPC says, oh, sea level is rising. But of course it's not rising, because you see the sand with this place is that place. The sand taken here, it is being deposited laterally. But it's laterally, yes, but also down, out to a lower level. So it's really a lowering of the sea level. And the old shoreline is seen here. That's the fossil shoreline of 50 years ago, and now starting to be overgrown. And in another island, we have this in island after island. In this island, you have a rock cat platform A, and then there's a present rock cat platform. You can see this is weathered. This one is fresh. And there's a fall at the round time. And because this one stays stable, if sea level would be rising, it would try to attack this and destroy it. And this is not the case. So here you have a long-term stability. You have this tree, which was standing in this ridiculous position. And when I saw this, I said, God, this is a fantastic tree, because it is a prison island, so they have looked at it and recorded it at least back to the earliest 50s, maybe at the end of the 40s, but at least to the... And if sea level would have risen just a little, it would be gone. And when I was there with the TV team to shoot the film, the Doomsday Called Off, the tree was lying flat. And I said, bah. So I was wrong, because that is how a scientist reacts. They immediately think, I was wrong. But then we have, up here there is a house where you can have tea and wonderfully grilled fish. So we went there in sorrow and sat down and had a little meal. And I asked the old friends, but when did the sea take the tree? And they said, no, the sea never took it. It was a group of Australian scientists. We pulled it down by hand. Nice people. Okay, then we jump to Bangladesh to see coastal erosion, and all these IPCC Boy Scouts, they would say, God, sea is rising in over a forest. Okay? But we have to look carefully, and then we see these type of trees. It's mangroves with horizontal roots. We know exactly where the mudflat was when it was eroded. We can reconstruct it. So the previous original mudflat curve before the erosion. So erosion, yes, but absolutely no sea level rise. And if you look a little more carefully, you see the old delta plane. It's even a little higher. And with other criteria, I can check that it was even lowering a little. Then we jump to Goa in southern India, where I recently did interesting work. You see the notch here, 60 centimeters above the algae rim. It's really absolutely clear. That's the high here. At the same place we have a harbor which is above, it is dried up and older, and we have a painting of that harbor. And we have, in that same painting, we have a lower harbor where the ships are lying. But in this one, it's not high and low tide because there are breaks. Then sea level as it rose, and we have here somewhere a rock cat platform, very extensive. You see it? But it's starting to be overgrown, and it started to be weathered. So it's not in operation any longer. And here you can see a change. Here the waves are attacking, starting to make a new one. So that's the present high tide level, and that's the past one. And this is dated by C40 now, and so on. So that is how we use morphology. And the same thing just around the corner. We have an old cliff with severe erosion. Now it's dead because it's overgrown and it's sand on sand. This is the higher rock cat platform. This one is the living algae now, and that corresponds to that level. That's the present one, and that is dead. And then we get this story in Bangladesh and Goa, which is very, very, very similar story. Very, very similar. But that's another thing, I will come back to that. But that is how we use morphology. And morphology doesn't lie. It's good. Then tide gauge is site-specific compaction, I have told. But then it's dynamics must be considered. Next slide. So this is the record from Mumbai. By the way, there you have the lowering, which I took morphological. This should be looked in this possible. This is a stable period, a rise period, a fall, and then 50 years of stability. That's the only way. This mean of it, mathematical mean, it means absolutely nothing. It's just a misleading long-term mean value. Just kick it out. It's unscientific, and it should never be used. So subtracting local compaction, we can do that. And I take the Venice, because here we have it's slowly subsiding area. Doesn't matter if it's subsiding. We are now checking the thing by subtracting it. There were the camera obscura studies where they had the algae rim measured also on the paintings. It's very consistent data about 1720. So the blue line is the subsidence or relative mean sea level rise. And superimposed on it, you have the tide gauge record. So you see, this goes very smooth here. There's not, if it would accelerate, it should depart from it. And when you come to 1970, where it should accelerate up, it's doing the opposite. There are some engineering things, but generally it's not acceleration. So we go to regional coastal morphology, fine for Indian Ocean. I have already shown this, because these were the dots I was at, but also St. Paul's and Perth. All these tells the same story, which I will soon tell you. And remember, even Kiribati, Tuvalu, and the other islands here, when you go to the record, it doesn't show sea level rise. But I take the observation of more than that. Very, very seamless. And it's a lot of geomorphological structure, which, as I tell you, you cannot play with it. Next one, mean values of numerous tide gauges scattered all over the world. So they had earlier 159 selected, and this is the distribution from uplifted area to subsiding area. You can see there is a flat here, maybe a little further on, and it is between 0 and 2 millimeters rise per. That's where most of the tide gauge is. That's where we have to be, and this is where IPCC is. It's up there in the rapidly subsiding area. They shouldn't be there. They should be down here. And then you could select things here. These guys are selecting things, and they can do that. But much better is to go to 204. And if you take out those outliers, it is 182 left, and the mean is 1.6 millimeter per year. So 1.6 is okay. But if anyone going above this is very, very strange, because then you upset the whole database. And still here, as we talk about, there is a much more subsidence hidden in it. So if anything changes, it's down. Okay. So then we do subtracting the crustal component from subsidence from the North Sea and Kattegat, and obtaining regional eustacy. Let's check this. The eustatic sea level is not rising in the North Sea region. We have this solution A, which is eustatic factor from the Amsterdam tide gauge, 1682 to 1930. I did this long ago by taking out the crustal components. And this is it. Then I went back to the Cuxhaven tide gauge, and they match more or less. It doesn't matter this change. But then I can add the continuation. Here it's a little problematic. But at any rate, it's not going up. For sure it's not going up, which the rest, or the Boy Scouts and IPCC are saying. So that is very important. And if we should accept the satellite altimetry of 3 or 3.2, those guys, which we are every geologist with any knowledge knows that they are subsiding. They have been subsided through thousands of years, maybe even millions of years. both those regions would be terribly rapidly uplifted, which is nonsense. So then we know that this is nonsense, which is another message. Then we go to Kattegat, my original area. Sweden, Denmark. This is the direction of tilting after this area went up with higher and higher. This area was the hinge, the axis of uplift on this side and subsidence on that. And this has remained stable for 8,000 years. Stable for 8,000 years. Therefore, if we go to that point and we have Nyborg here, wow, that is a place to look for real, actual geostatic sea level. And Korsør on the other side, we could check them, how they are. So let us do that. So we have the Nyborg, which is 1.1. So that must approximate geostatic sea level. That's a good, I mean, it's better than anything else. There's nothing in the world which is better than that figure, as a matter of fact. Then we go to Korsør, which is, we have an uplift of plus 0.1. So we have to add it, as a matter of course. And then you go for 0.9. So 1 to 0.9 millimeter per year, right? That is the sea level component here, absolutely for sure. And it cannot be higher. It might be lower if there is some subsidence involved. But this may be the difference here, okay? But this is a strong thing, so nothing more than that I think we can guarantee. So next one, Earth rate of rotation, which is interesting. Of course, as a function of the ocean radius changes, when the arms of the figure skater is, no, this figure skater, she is twisting around with a very high speed, arms like this. And when she slows down, she delicately put out her arms and go down. And that is a law of angular momentum. So this was the Amsterdam curve I showed you earlier, observed. And if you compare with the length of the day, the rotation, the centennial part of it, it fits very, very well with a little lag time. Really excellent. But if you do the same trick up here, it doesn't work at all, because rotation is going on, down, more like sea level is lowering, rising. There's nothing supporting a rise. Then we come to satellite. It's invalidated by subjective corrections. And it's interesting that Envisat, the European satellite, only shows 0.4 when they see the high. So there is something rotten, not in the state of Denmark, but in the state of those people who are working here. So in 2000, we got the first nice record from the satellite altimetry. There is absolutely no rising trend. This is a variability, but on the side. Then we have the ENSO event here with opposite, and it's more or less. Maybe it's something rising, but we couldn't see it. So we had a satellite reading. You have the instrumental technical adjustments, and then you get the zero, as it was here to begin with. And then the gravity, which I will show, showed this. So it seems that we are here, not at all up there, because they had personal calibration, they call it, but it's correction of that. Then you go up to around 3. So there's something rotten here. Okay? Then we go to GRACE, which is gravity experiment. It's also wrongly calibrated. You have the raw data, which show a very tiny fall off, but it was calibrated by this global isostatic adjustment. What kind of thing is that? Then we go to the global loading model. This guy back there. It is time to go into questioning of this, because it is a thief in the system. So there are two ways of looking upon it. The old ones, which I also, then you have a regional isostatic, when you add the ice cap here, it is being taken care of by horizontal displacement. So when it's going down here, it's popping up here as the forebulge. Okay? And in Fennoscandia, it's absolutely clear. It's no doubt that it's there. We can see the rates, how it's coming back and it's flowing out, and we can see the mass in the which being displaced down is the same as the mass in the forebulge. So here it's really a nice story, but that might not be the case in America. We could. So the other loading model said that it's the linear viscosity. Linear viscosity. So the load here is being transferred all over the globe, and it's popping up here all over the places. And that is the correction which they apply. So we go to the next one, the Gaia, to be questioned. The near field tested in Fennoscandia, it fails because this doesn't work. New data support the low viscosity. There's really many new physical things that happened in the last years. It is referred to in my paper in Earth and Environmental Science. The far field there, the sea level data in India, it also fails. And 147 far field tide gauges show remarkable little correlation, according to Youth and Dean. And that's the only thing we have. The Gaia correction of the satellite gives 3.2, and which is completely impossible from the other guy. And of course, just this impossibility invalidates the measure. There must be something wrong with it. The 2.32 millimeter of corrected JSON data should be almost the same as 0.40 of the uncorrected NVSAT. So there's something wrong here. And the Grace correction of it invalidates the message. The tide gauge chosen in Hong Kong to record level represent a strongly subsiding area. So I think we should have to question this. We are now ready to sum up the facts. Are you ready? Yes, we are. Okay. The present is a reflection of the past. Nothing more, nothing less. Just the same old story. Geostatic sea level records. We have Stockholm and Connecticut because they are very well, very detailed. And I can stand for those. The A1, what is this? They said ups and downs as usual. Nothing unique today. See, those rises are much larger than what happened here. There's almost nothing. And if you go to the Connecticut code, there is an uplift, is a rise here after the Little Ice Age, and it's a high here and a high there. The rise here is much faster than that rise, and it's even higher here. Then back to this record, the NOAA, which is very nice scatter of sea level. I have shown you that many global key sites give really zero rise, like in the Indian Ocean and the Pacific Ocean. It's really, you don't find anything there, not even the tide gauges. And what I showed you in the morphological, I think, is strong values. But the mean of the 280 tide gauge, they are here. So we can accept that. Somewhere in between here, we can play. That's okay. There's nothing wrong. There is different opinions. Those things are wrong. We have to kick it out. And the same, of course, with IPCC's idea. They are not using proper basic material. Basic material here. And you can be doing whatever there. It's, of course, very interesting that 10 millimeter per year or a little less was in the Kattegat. And that was really the best one. So what is the global usage today? Yeah, we have, this is the 8.6. If it continues here, I put it here because the other graph and the model curve here, you can add it from here. It's 1.6, 182 tide gauges. From 92 up, there comes an enormous rise with double the rate of the satellites. That's, of course, out. It could be the maximum. But much better is, for example, 10. If you can put it there, you can even put it a little higher up. Doesn't matter. But 10 or oh, we are there. It has to be between this and that. That's the largest thing. And then, but most probably between +10 and 0. That's the best we can do today. And that is nothing frightening. And if you put it in the context of those be now questions, and they have polluted the work. This is the rates, observation fact. We are here for between 0 or maybe 10. In the near future, we are not going to go to higher rates. Everything points to that we will have a new solar minimum by about 2040, plus and minus 10 years. And there's no way we can escape it. When the sun is there, it's a function of the sun. We cannot switch off the sun. We can switch off our computers. We can switch off our brains. Obviously, some people are doing this. But they want to go up here with enormous rate. I mean, from here, we should be up here, and Ramstorff are up there. And that is the ultimate frame. Nothing should be above that one. These are the IPCC estimate. This is the inquiry. We are here. So sea level by the year 2000 estimated to be only 5 plus and minus 15. That's not the problem. That's not the problem. And the sun can't go on shining. Without a flooding concept, there is not much left of the threat of IPCC. The tiger has lost its teeth. Maybe it was not even a real tiger, just a blown up balloon dummy. And of course, I have written a little pamphlet here with a modest title, The Greatest Lie Ever Told. And in order to get the next next issue revised, I have to, but I have some copies with me. And then it has come in recent, just here 2 days ago, they took this as a solution. For me, this is not a solution, it's another, because this is not the thing we have problems, disaster, and waste. We have to go other ways than that. We can be against both of it. This is a few relevant papers. This one may be the latest one with respect to sea level. And then, of course, I dedicate my talk to the Polish people who understand that the IPCC measure is totally rotten and twisted. Thank you.